For mine here. This serves as we're continuing our the lesson on chapter 3. Let's see, hang on. Exponential and logarithmic functions. And so this is section 3.2, log functions. So a few objectives. We like to define logarithmic functions. We like to evaluate logarithms, find the domains of log functions, graph the logarithmic function, use logarithms to solve exponential equations. Okay. So the definition of a log function for a positive x and a positive a and a not equal to 1, we say that y equals a log of x base a if and only if x equals a to the power of y, right? So in the past, we've kind of had this discussion on exponentials, right? Exponentials have a horizontal asymptote, and they kind of start off kind of running along the top side of the horizontal asymptote. Then they pass through the point 0, 1, right? And then they grow exponentially. If you were to take that image and rotate along the diagonal y equals x, right? So it kind of rotates on the diagonal, then now we can start to look at the graph of the inverse function, which is the log, right? So logs have a vertical asymptote and they start off to the right side of the y-axis, kind of running along the y-axis, and then it passes through the point 1, 0, and it kind of, it seems as if it flattens out as it goes to the right, but it actually doesn't. It continues to gradually increase, right? So I say that to say that logs and exponentials are inverses of each other. So we can rewrite these logs in exponential form, right? And for right now, in order to do this, you take this base a and swing it to the other side, and it becomes the base of the exponent, right? So this base swings over. Now you have a to the power of y, and then on the other side, the only thing that's left is the x, right? So I guess function f of x equals log of x base a is called a logarithmic function with base a. The logarithmic function is the inverse function of the exponential function. Okay, let's try another one. So write each exponential equation in logarithmic form. So the same way to go from log to exponential, we swung the base of the log and it became the base of the exponent. Then you can basically reverse that to reverse that process to undo it, right? To put it back. So if we wanted to write, it didn't feel like it was in my way like that before, and it just seems like as of late. Exponentials as logs, for instance, the base for part A is the 4, so it's going to swing over, become the base of the log. So when the 4 swings, now we're going to have log of 64 base 4 equals 3, right? Base of the exponent swings and becomes the base of the log. So then we're going to have log base 1/2 of 1 by 16 equals 4. The log of 7 base a equals -2. (64 base 4), right? In exponential form. So now we're going to go from, we went from exponential to log form. Now we're going to go from log form to exponential form. If you write these logs as exponential, the base swings, the base of the log swings to the other side, it becomes the base of the exponential. So then for A, to the power of 5 equals 243. Two to the power of x equals 5. A to the power of x equals n. We want to evaluate logs, find the value of each log, right? So for each one, what I'm going to do is set each one equal to y. All right. If we set them equal to y, then we can kind of repeat what we just did to solve. For a, if we rewrite this as an exponential, over 5 to the power of y equals 25. So then you have 5 to the power of y equals 5 squared. So then y equals 2. Okay, I'm gonna need some space. The two swings, you have 2 to the power of y equals 16. So 16 is what? 2 to the power of 4. One third to the power of y equals 9. So I'm going to go ahead and write 9 as 3 squared. So 1 over 3 is the same as 3 to the power of -1. A power raised to another power, you multiply, right? So we have 3 to the -1, 3 to the power of -1 to the power of y. It gives us 3 to the power of -y equals 3 squared. Notice we're getting those bases to be the same. So then if -y equals 2, that means y equals -2. C, and for part D, 7 to the power of y equals 7. There is an implied 1 here. Right? Equals 1. If there's 6 swings, we have 6. Why does that feel weird? 6 to the power of y is the same as 6 to the power of 0. So then y equals 0. The 4 swings, we get 4 to the power of y equals, I'm going to rewrite as 2 to the -1. I want to get these to the same base. So 4 is the same as 2 squared. Again, a power raised to another power, you multiply. So 4 to the power of y is the same as 2 to the power of 2y equals 2 to the power of -1. Divide both sides by 2. Y equals a -1/2. move all of this to the next page. Two, 1, 0, negative 1 half. 2, 4, 2, 1, 0, negative 1 half. 2, 4, negative 2, 1, 0, negative 1 half. 1, 0, negative 1 half, right? Okay. Okay, so we can use a similar technique or the same technique to solve these. So we're going to solve these laws by rewriting them as exponentials, right? So yeah, the base is going to swing there by rewriting them as exponentials. A equation is going to be the same as equals 5 to the power of a negative 3 over 125. This technique called the change of base formula. If we said the log of 1 over 125 divided by the log of 5, we'll get 3, right? It's not going to do it right now. It's because it's coming up and we'll see it momentarily. Part B. Exponential 3 to the power of y equals 1 is 3 to the negative 3. Y equals negative 3. Up there, but you should be able to make the connection if you think about it. Right? I don't know what we've been doing. C. Z to the power of 3 or Z to the power of 3. That's going to be, and 1,000 we can write as 10 to the power of 3. So then Z equals. We might need some more space. Yeah, let me give myself some space. For part B, let's move this guy. Squared minus 6x plus 10 equals 2, right? Because it's 2 to the power of 1, which is just 2, right? So this is just solving the trinomial. We can set it to 0 and factor if we subtract 2 from both sides. We'll have x squared minus 6x plus 8 equals 0. So then we're trying to see, can we factor this into some form like this, where we have x and x here? Because this is a plus, if we're looking for two numbers that multiply to give us a positive, then that both of our signs are either positive or both our signs are either negative. And this tells us the sign of the larger number. So then it should both be negative. Two numbers that multiply to give us 8 and add to give us 6. What is it? 4 and 2. Negative 4 times negative 2 is 8. Negative 4 plus negative 2 is 6. We can use this technique called the zero factor property. When two or more things multiply to give us 0, long story short, you set each thing to 0 and solve. So we would get x equals 4 or 2. This, we can plug in, if we say in the calculator, what we would do for that one is we let x be 4. We say log of when x is 4 divided by the log of 2, and the answer should be 1. And then if we say the log of when x is 2 divided by log of 2, the answer is just still 1. Okay. We got 1 over 125, negative 3, 10, and then 2 and 4. Negative 3, 10, and 2 and 4. The log, right? So keep in mind that because the log is the inverse of the exponential, the domain of the exponential was what, all reals, and the range was 0 to infinity. So because it inverses, that means that the domain of the log is 0 to infinity, and the range of the log is all reals, right? So basically switch places. So once you are clear about the domain and range for exponential, as long as you can reverse those, then you get the domain and range of the log. So logs of zeros and negative numbers are not defined. So the domain of log is restricted to strictly positive numbers. Okay. So again, for log, we can't take the log of a negative. So in order to find this domain, this 2 minus x has to be strictly greater than 0. We add x on both sides. Less than 2, right? On both sides, we have 2 is greater than 0. Notice 2 is still greater than 0. So then this is set notation, if we wanted to write this in interval notation. So we're talking about all the numbers to the left of 2. So the far left would be negative infinity up until 2. Infinity always gets a parentheses. And because there's no bar here, that means we use a parentheses. If there was a bar, then we would use brackets. This means we get really close to that number, but we don't actually reach it. A bracket means we get really close to that number and we actually do reach it. We include the number. Okay. X has to be strictly greater than 0, so 2 is greater than x. Negative infinity to 2. Properties of logs for any base A that's strictly positive and not equal to 1. And the log of a base A is 1. Again, if we did change of base formula, this is like saying the log of A divided by the log of A, and they essentially cancel. The log of 1 is 0, okay? So log and exponentials cancel each other out. So the log of A to the power of x, the exponent goes in front, and then it's basically x times this guy, that's why it's just x. And again, logs and exponents are inverses of each other, so these guys cancel each other out, and it leaves us with just the x. The notes on this one, it asks us to sketch the graph. So the first method, let me see, we chose values of x. Let me see. If I were making this chart and doing it myself, it would probably be a little bit easier to choose values of y here, right? Because these values of x are not obvious, but the values of y, like you can go let y be negative 3, negative 2, negative 1, 0, 1, 2, 3, right? So then, for instance, if y were negative 3, and then say we rewrote it as an x, well, if we were solving for x, if y is negative 3, if we swing to 3, then we'll have 3 to the power of negative 3, and that's where this comes from. If y were negative 2, we would have 3 to the negative 2, that's where this comes. This is 3 to the negative 1, 3 to the 0, right? So if I were making a table, to me, it would be easier to start with choose values of y and find the corresponding x values. Let's make a table. So then once you have your x's and your corresponding y's, you can just plot them and you get something like this. This is the general shape of a log. Generally speaking, with like little to no manipulations, the logs pass through the point 1, 0, right? This guy here. There's a vertical asymptote. So we start off slightly to the right, running along the right-hand side of it. We pass through the point 1, 0, and then it goes off to the right. And it doesn't, there's no horizontal asymptote, and it does not flatten out. It's always going to be steadily increasing. It looks like it flattens out, but it doesn't. So then method 2 is if you wanted to graph, just write it as an exponential to begin with, right? So we were given, actually, they didn't write it as an exponential. They actually found the inverse. Like, it's very subtle between finding the inverse and using the inverse. It looks the same. This is the inverse function, and then once you have the inverse function, you use your x's, find the corresponding y's. Then you can actually just switch the x and the y's. All right, just switch all of them. So like if you choose, like for instance, like if x was -3, -2, -1, you find the corresponding y, then you just switch those columns, and that'll be the graph of the log. All right. So that's another technique. You can use the inverse function to find your function. So to kind of a brief recap on some properties of exponential and logs. So the domain of exponentials is all reals and the range is 0 to infinity. If you reverse those, this is the range of your log and this is the domain of the log. Exponential functions, the y-intercept is 1 and there's no x-intercept. Log functions, the x-intercept is 1 and there's no y-intercept. All right, it's kind of that whole switching. Exponential functions have a horizontal asymptote, which is the x-axis. Log functions have a vertical asymptote, which is the y-axis. Exponential function is 1 to 1, which means it passes a horizontal line test, which means it has an inverse, right? And this is how we verify that a function is 1 to 1. You know, we choose 2 different values of x, show that they have 2 different values of y. That implies that the x's have to be equal, right? If we set 2 different values of y equal to each other, then that shows that the 2 values of x are equal to each other. Same thing here. The u and the v, then they're equal. So these are graphs of the log function. Again, the general shape is this guy here. And then this is like where the base is between 0 and 1. So you have a log function that behaves this way. Generally, it's increasing like this. But if that base is between 0 and 1, then it behaves in this fashion. Okay, start with a graph of log of x base 3 and use the transformations to sketch the graph of each function, right? So log of x base 3 is similar, the shape is similar to this, right? So now the idea is just start with a shape like this and then describe your graph through transformations. So for instance, transformation here, we added a 2 on the outside of our base function, right? So outside manipulations generally cause a vertical change. So this should shift it up by 2 units. So instead of passing through the point 1, 0, it should pass through the point 1, 2, right? So we can shift the whole graph up by 2 for the first one. Let's see if we got it here. All right, see, it shifted up by 2. For part B, we subtracted 1 on the inside of our base function, like within the parentheses. So inside manipulations generally cause a horizontal change. This should move it, and it's typically the reverse of our intuition. Like for the first one went along with our intuition. We added 2, it went up 2, all right? But see, this one, we subtracted 1 on the inside. You may think it goes in the negative direction being left, but it's actually the reverse of our intuition. So this one should go to the right by 1 unit. All right? So that one should go to the right by 1 unit. See it here. Shift to the right by 1 unit. This one, we multiply the outside of our base function by a negative. So outside manipulations usually cause a vertical change. So this one should flip vertically over the x-axis, and the last one should flip horizontally over the y-axis. Okay. Domain in the graphical sense. So the pink graph is our graph. The domain is the very left to the very right. So since we just moved it up, the domain is going to stay the same. And since the range of the log was already all reals, moving it up and down, the range is still all reals. Okay. So for part C, we said flip vertically. So we flipped it top to bottom over the x-axis. So reflect over the x-axis. So this this one flipped over to y. Could be inside. So this one, because we flip horizontally, instead of going from 0 to infinity, now it goes from negative infinity to 0. And the range stays as always. Let's see something. So then the common log, so logarithm of base 10 is called the common log. It's denoted by omitting the base, right? So if you see a log with no base written, then there's an implied 10 there. So that's the common log of log base 10. So thus y equals log of x if and only if, again, if we swing the implied base 10, y equals log of x is the same as x equals 10 to the power of y. And then we still have this recurring theme of basic properties. So sketch the graph. So this one, I'm just going to list out the transformations. We're still starting with the general shape of a log, right? And I'll just do a quick sketch. So here's your x and y plane. And general shape of a log is like that. $7 profit, 290. Sure. So then, to list out the transformations, we can work our way from the inside to the out, all right? So the first transformation, we subtracted 2 on the inside, so that should cause a horizontal change. So the first transformation, it should go to the right 2 units. Next, we multiply the outside by a negative, so it should flip vertically. And then we added the 2 on the outside, so that should shift it up 2 units. So we go right 2, flip top to bottom, and then go up 2. So if you go right 2 there, if you follow the vertical asymptote, it said flip top to bottom and then go up 2. And the pink is the final graph. So then the logarithm of base e is called the natural log and is denoted by ln of x. So that's going to be this guy here, log base e of x. So then if we have y equals the natural log of x, if and only if the base e swings e to the power of y equals x. And then the same recurring 4 properties. So evaluate the log. So again, here, what I'm going to do is set each one equal to y and use our swinging base technique. Right. So they all have an implied base e. I'm just going to kind of identify it like this, and I'm going to swing that base e for each one. Okay. So then for part A. So this is log base e. If the base e swings, we're going to have e to the power of y equals e to the power of 4. So then y equals 4. We're going to have e to the power of y equals, now we got 1 over e to the 2.5. So I'm going to rewrite that as a negative exponent. All right. So then we get y equals negative 2.5. Part C, we have e to the power of y equals 3. That one actually, just use a calculator. So that one I would just in my calculator, just do the natural log of 3. So let me get rid of, I don't think we need this part here. There. The last one we said use a calculator. How long will it take to double your money if it earns 6.5% compounded continuously? So for part A, for continuous compounding, there's this formula we use. I call it PERT. I think we discussed some compound interest formulas, right? So when it's continuous compounding, PE to the RT, PERT, right? So if it says how long, that means we're solving for T to double your money. So that means we want to finish with 2P. We're starting with P. E to the if it earns 6.5%, that's the growth rate. Then 6.5%, we have to write as a decimal. So the percent symbol, you can look at it as per 100. So we divide by 100. So then the 6.5 turns into 0.065, and we're solving for T. Okay. Divide both sides by P. Hello. That out of the exponent, you take the natural log on both sides. Right? So then we have 5t equals the natural log of 2. I did kind of switch things around just because I wanted my variable on the left. I took the natural log of both sides. T is going to be equal to the natural log of 2 divided by 0.065. Calculator. Natural log of 2 divided by 0.065, 10.664. Current compounding continuously with your money double in 5 years. Okay, so now they're asking us to solve for R. I think I have enough space. So then for part B, we want to finish with 2P. Okay, so here, I'm going to go ahead and use a shortcut. Let me see. So that's we saw an example using PERT. If we're talking about doubling our money, then there's there's a shortcut you can use. It's KT equals the natural log of 2, right? It's like the doubling time formula. Let me see if this works. KT equals the natural log of 2. All right. So, and we actually used it in the last one. If we wanted to double, we wanted to solve for T, they gave us the 0.065, so it was the natural log of 2 divided by 0.065. If we want to solve for the rate of return, in this case, I'm just calling it K, but the K is our rate of return. But now we have 5 years. 5 years. Then our rate is going to be the natural log of 2 divided by my battery's low. log of 2 divided by 5. 0.863%. Man, that's high. Percent. Mm, 10.6 or 10.7 years and 13.9. This law of cooling. This is interesting because this is the same thing. Like, so I'm kind of pausing because these are some of the same topics we're talking about in my calculus course. So yeah, it's, even the calculus students are using the same material, right? It's math is all like steps on the ladder or a pyramid. You can't talk about that stuff without knowing what you all are doing. Newton's law of cooling states that this T, the T equals this, where T is the temperature of the object at time T. T sub S is the surrounding temperature, and T naught is the value of T when the time is 0, right? So the surrounding temperature, initial, let me see, the temperature at time 0, right? Okay. And T is the temperature of an object based on time, and then you have the surrounding temperature and the temperature when time was 0. So the local McDonald's franchise has discovered that when coffee is poured from a coffee maker whose contents are 180 degrees Fahrenheit into a non-insulated pot, after 1 minute, the coffee cools to 165 degrees Fahrenheit if the room temperature is 72 degrees Fahrenheit. How long should the employees wait before pouring the coffee from this non-insulated pot into cups to deliver it to customers at 125? Okay. T is the temperature of the object based on the time. So however long we wait, that'll give us the desired temperature. Let me get a copy. Let me just write it. T equals T sub S plus T naught minus T sub S e to the negative KT. Okay. So some space. Rapidly approaching the end of the section. I know it's a little bit long. For little t, when coffee maker whose contents are 180 degrees Fahrenheit into a non-insulated pot, after 1 minute, the coffee cools to this. So should they wait before pouring the coffee? So it seems like we wanted to finish the temperature of the surrounding. When the coffee is poured from a coffee maker, the room temperature, right? Okay. It's 72 degrees Fahrenheit. Let me, before I plug these in, let me write out everything. So it seems like the desired temperature is 125 degrees Fahrenheit. The temperature of the surrounding 72 degrees Fahrenheit. The temperature at the start, let me see. It looks like it's 180 degrees Fahrenheit. The rate, let me see. $65, what is that? After 1 minute. So whose contents are into a non-insulated pot after 1 minute, the coffee cools to 165. So then after 1 minute, it cools to 165. Okay. Let's plug in, that ordered pair, let's hold that off to the side for right now. Well, we can plug that in. We can use that to solve, because the only thing we're missing we have capital T, we have the surrounding temperature, we have the initial temperature, we have this guy. We're trying to ultimately solve for little t, but we don't have the rate, right? So we can use this ordered pair, plug that in. Only thing we'll be missing is the rate. Once we have the rate, we can go back and answer the question. Okay. So let's solve for k for right now. So right now we're just solving for k. Plug in that ordered pair. After 1 minute, the temperature is 165. So the surrounding temperature, 72. The initial temperature is 180 minus the surrounding temperature is 72. And the time has been 1 minute. So e to the negative k, right? Okay, so then if we subtract 72 on both sides, on the left, we get what, 3, what is that, 9? Okay. 80 minus 72, what is that? Like 108? E to the negative k. Divide both sides by 108. E to the negative k equals 93 over 108. So then here we take the natural log on both sides. Natural log of this, natural log of this. These guys cancel, and that kind of forces this to come down. So then we have negative k, the natural log of 93 over 108. And then long story short, k is going to be equal to the negative natural log of 93 over 108. Okay. I can crunch this number, but instead of crunching that number, I am going to leave it like that so I can keep it exact. And now we can go back and temperature of 125, right? So now I'm going to go back. Desired temperature of 125. So 72, 180, 72, E. Now we just, so I'm just gonna label this as star. Star times T. Number. I'm just not crunching it until, so basically, I don't even know how I pulled that menu up. I wish I know how I did that. Because there are times when I want to pull up, and I tried researching. I had to try to figure that out. Let's solve for T. Let me get this. I'm going to subtract 72 from both sides. Let me see, that's a 3, 5. And then 108. We get e to the negative star t over 108. Okay. For the exponent, we take the natural log on both sides. And remember, star is just a number. Right? I'm just trying to keep it exact until the end. So then we have negative star t, natural log 53. Long story short, t is going to be equal to negative natural log of 53 over 108 divided by a star. And so we said star so jumps a little bit more. This one's positive, and let's crunch that number. So let's see, what do we get? So we get approximately, and this should be in terms of minutes. Okay, so double negative is positive, so then it should just be the natural log of 53 over 108 divided by the natural log of 93 over 108. 6. See, how do we do? T naught is 180, surrounding temperature 72. I think we got all of this. No, we didn't crunch that number. Right, 4.76. A model. And this is similar to PERT, right? So exponential growth is like PERT. A is the quantity after some time t. A naught is the initial or starting amount. R is the rate of growth or decay, and T is the time starting from time 0. In a large lake, 1/5 of the water is replaced by clean water each year. A chemical spill deposits 60,000 cubic meters of soluble toxic waste into the lake. How much of this toxin will be left in the lake after 4 years? When will the toxic chemical be reduced to 6,000 cubic meters? Okay. So let me see. A not e to the, I'll just say RT, all right? How much of this toxin will be left in the lake after 4 years? Okay, so let's see if we can plug in the different components. Let me give us space. Replaced by clean water each year. So for part A, it looks like our A naught is 60,000 cubic meters. A rate, because it's kind of being filtered. Rate is a because it's it's getting diluted, right? Time is 4 years. The amount left after 4 years should be 60,000. The rate, I'm going to do this negative 1/5. Right. And like, because I was a little bit hesitant, should it be positive or negative? I mean, negative makes more sense because we're decreasing the amount of this thing. Let's go ahead and do the negative 6123 times e to the power of a negative 1. Let's do it like this, parentheses 1/5. With a negative exponent, it should be less than 60. Okay, and then just to convince ourselves, if we use a positive exponent, which is larger than 60, all right? Okay. The one that we think is correct, which is this one. How much? So we're going to calculate 959.74 cubic meters. We reduced to 6,000. So now they're asking us to solve for t. We want to finish with 6,000 cubic meters. We start the 1,000 cubic meters. E to the, we got a negative 1/5, and we're solving for t. How long will it take for us to get there? Okay. Divide both sides by 60,000. So 6 over 60. It reduces down to 1/10, right? So if you divide both sides by 60, on the left, you're going to have 1/10. On the right, we're going to have this e to the negative 1/5 times t. If we want to get that out of the exponent, we take the natural log on both sides. Okay. Here, natural log here. These guys cancel, and that brings us out of the exponent. And we can leave that as the natural log of 1/10. We'll get a 5 equals the natural log of 1/10. So to solve for t, long story short, multiply both sides by 5, by -5. So then we're going to get -5 times the natural log of 1/10. How's the that's not natural log of 1/10. Years. 11, about 11 point, we could say 5. I'm going to say 513. So 11.513 years. Okay, we got 11.513. So I think we got that same thing, 26 and 11.513. Okay. Oh, I thought we would have had something there. The end of the section. Yeah, so we explored like logs and exponentials. We only have a few more sections left in this chapter, and we'll continue next time. And with that, that brings us to the end of the section. And from one beautiful mind to another, enjoy the rest of your day. Okay, take care, guys. Peace.